Hey, everyone.
Hey, good morning, Joe.
All right. So I have one agenda item that was requested for today, which is the um, OPI EVPN bridge architecture. This is the new repo that's been created. Um, so do we have, and the only, I guess, announcement I have, which I didn't write down, is that give me 1 second to double, I have to. Okay, sorry. I have only one announcement, which is uh, Chris Murphy will no longer be the board chair. Um, and I don't know who the replacement is yet. But
Uh, it's a Rashid Khan. The replacement is Rashid Khan.
okay, that's fine. All right. And it's not for any reason. So she announced she's leaving Red Hat. So that's why, not for any other reason. Okay. So do we have any other announcements or agenda topics? All right, and just double
Sorry,
check.
I couldn't unmute there for a sec.
Oh, yes.
Triple muted. So not for today, but for next week, we would like to come in and have a bit of a discussion around trying to get some agreement on some foundational pieces across the different working groups. From an infrastructural point of view, from an OPI API point of view, and from a most basic kind of use case. We think that there's a bit of a gap potentially, but it'd be good to, get agreement across the board on what the most foundational pieces would look like.
Okay.
Okay. So I'll put that on the schedule. Anything else? Future
Sure.
agenda items? Anything else?
Joe, this is Paul. Just a real quick agenda item or announcement. We had in the outreach group, we had been planning on using the SmartNIC Summit as a vehicle to have another kind of half day get together and that sort of thing in San Jose. I contacted the SmartNIC organizers, and they are not going to be having a SmartNIC Summit this year. So we won't be doing that at SmartNIC Summit. We'll talk about that in the outreach group next week, and see if we can come up with an alternative venue to do something like that.
Okay.
That was simply an announcement. So there you go.
Yeah, there we go. Anything else?
Just that I'll put in the chat window. I need inputs on the SOW so that I can take this forward, so that I can get some external parties to engage on this software maintenance aspect.
All right. All right, I'll paste that in there.
Joe, a small announcement from me at the use case group. We now have approval from Entity Lab to use their name when talking about distributed UPF, and they're in the process of getting us approvals for the code, but that will take a little bit of time. It's going through their corporate approval process, which is not easy, but they are going through the motions. But the good news is we can openly say that we're working with Entity Lab on the distributed UPF use case.
A lot we can talk about it offline, but does that merit a blog post and
Yeah, I wrote inside the Slack for the outreach group that we can now say at Mobile World Congress that we're working with NTT.
Yes. That'd be great. We'll do that. Wondering if it merits a blog post though. Is it something you or someone else would write?
Yeah, I can definitely write that. I want to go past one more checkpoint, which is them saying when we'll get the code, and then we can do a blog post about it. But again, saying that we work with NTT, and of course now I'm pushing them to join OPI.
Yes.
This is the next step because we already have Fujitsu. If we have NTT, it will be a perfect storm.
Okay. Sounds good.
All right. All excellent information. Anybody else? All right. OPI EVPN bridge.
Yes, hello. Can I take the screen?
Yeah, just give me one moment. All right, please go ahead. The floor is yours.
Okay, thank you. Let me just... Okay, I will just share my entire screen. It's difficult otherwise. Can you see my screen?
Yes, we can.
Yes.
All right. Hello, my name is Dimitrios Markou. The purpose of this presentation is to present the new architecture of OPI VPN bridge that we intend to upstream to the OPI VPN bridge repo that we have in the OPI GitHub. I'm just for some background, I'm a senior cloud open source developer in Ericsson and a driver of the upstream workstream inside the Intel Ericsson proof of concept that it runs internally, and it is about the VPN gateway offload to IPU, DPU devices. I would like to ask kindly if you can just wait, if you have any questions, wait for me to actually finish the whole presentation because I have several stuff to present. And then I believe we will have enough time to actually address any questions that you have. And the general purpose of this meeting is to actually present the architecture and the whole design and the purpose of it, and also gather any feedback that maybe you have to share with me. So a bit of the agenda for today, we will have an overview of the Intel Ericsson IPU POC. Just to give some context, then the network architecture, the Kubernetes tenant networking, and the VPN gateway design, where we are going to talk a bit and present the VPN gateway API that has been already accepted by the OPI entities merged to the OPI API project. The target architecture that we have, and then we will focus on the OPI VPN bridge architecture. I will present also some sequence diagrams that I have there, and also some references, a reference slide. So the overview of the Intel Ericsson POC is that Intel and Ericsson working together on several IPU-based use cases, which are around telco edge networking for Kubernetes, remote manageability of the IPU, and network security also. And if we focus more on the networking use cases, right now we support Kubernetes primary and accelerated secondary networking, as the latter is critical for telco use cases. We need an integrated edge router and also a managed underlay on the IPU. The integrated edge router is called EVPN gateway in our case. All the control planes that are consumed are based on open source project, and they are installed on the IPU ARM cores. And we were using an open architecture that is based on standard interfaces, and the goal is to contribute a general vendor agnostic code to the OPI community, so we can actually integrate other vendors except from Intel. So this is the overview, and if we move on to the network architecture, what we see here is that on the right-hand side, we have a single server deployment that is equipped with an IPU or a DPU there, and on the IPU, we have offloaded any VPN gateway functionality. This single server deployment can be a telco edge site or an enterprise site that runs any kind of application, 5G application, cloud run applications, and other similar stuff. And the main goal is to connect this single server deployment to the central site where you have your data center there and you have some PE routers, and you want to connect those workloads, those single servers, to the central data center site. In order to do that, we are going to use the EVPN protocol, which supports layer 3 and layer 2 VPN overlay. And by that, we will have some BGP peering as control plane between the EVPN gateway function that sits on the IPU and the PE routers. This is our control plane. Then the data plane where the actual traffic runs, it will be VXLAN encapsulated. And also, because we are using IP arbitrary transport networks, then if we want extra security on that, we will support also IPsec encryption in the whole thing. So this is the networking architecture. And if we say a few more words around the Kubernetes tenant networking and the VPN gateway design that we have, here we see the EVPN gateway API that is already merged and approved by the OPI community. Generally consists of 4 objects: a VRF, an SVI, a logical bridge object, and a bridgeport object. And if we go a bit to more details on those objects, we can start from the logical bridge, which is a general local layer 2 broadcast domain, which can optionally connect it to a layer 2 EVPN instance if we use the layer 2 VNI parameter in that object. Then we have the bridge ports that what actually do is attaches a virtual functions to one or more logical bridges that we have, and it can be 2 types. It can be a type access if we just connect it to a logical bridge with in an access way with untagged VLAN, or it can be a trunk type where we connect one or more logical bridges in a VLAN tagged way. Then the next object is the VRF, which is a local routing instance for a layer 3 VPN, and it is identified by the layer 3 VNI parameter that we have there. And also, lastly, we have the SVI object, which stands for Switch Virtual Interface. And what exactly it does is that it connects the logical bridge to a VRF for layer 3 VPN functionality. Actually, it is used to connect a layer 2 broadcast domain to a layer 3 routing domain. So this is the already merged EVPN gateway API that we have. And if we check a bit the target architecture, So here we can see the host, and at the bottom we have our IPU or XPU. So in the host, we have a typical Kubernetes deployment where you have your primary networking that is provided by the primary CNI there, the kube proxy, and the Linux routing IP tables for providing primary connectivity to Kubernetes pods. Also, through Multus, we inject secondary virtual functions inside the Kubernetes pod for having secondary networks consumed by those Kubernetes pods. And we can see at the bottom, we have like the IPU or XPU, where we have two physical ports, which each of those have a capacity of 100 gigabyte each, and provide external networking functionality to the virtual functions that are exposed in the host by a programmable hardware pipeline. So this is where the VPN gateway offload functionality sits. We have several stages in that pipeline. We have a VLAN-aware layer 2 bridge. We have the VRF routing section. We have the VXLAN NCAP decap section. Then it's the other layer routing, where what we call global routing domain, really. And also you have the encryption decryption stage, where we use IPsec encryption. So this is the programmable hardware pipeline. And in order to actually program this pipeline, we need to have some management plane. So on the left-hand side, on the ARM cores, we have the OPI VPN bridge. This is the main component that we are going to talk today. That's why you see it in the red cycle. And what the OPI VPN bridge does is that communicates with a different and cooperates with the different control planes that sits on the ARM cores. For instance, Linux bridging and routing, which is what we call slow path. This is one control plane. The next one is the VPN gateway control plane, which is based on FRR today, and also the IPsec control plane, which is based on StrongSwan. So the OPI VPN bridge actually fetches the forwarding intent by those different control planes, cooperates with those, and actually translate that forwarding intent to P4 rules through the vendor plugin or other rules through that vendor plugin. And the vendor plugin takes care of the configuration of the programmable hardware pipeline, which in our case in IPU, it's a P4 based programmable hardware pipeline, but in NVIDIA, for instance, for a DPU, it can be a different way, like RTFlow or something else. So this is what's happening on the IPU with the ARM cores. Then at the top, we have the VPN gateway CNI. This is a CNI that we have developed, and it is used in order to inject the secondary virtual functions inside the Kubernetes pods, and also configure the P4 hardware pipeline through the OPI VPN bridge in order to enable the networking communication towards those secondary virtual functions in the Kubernetes pods. Those secondary virtual functions can be of two types, as I said, can be access or trunk if we need access to just one network or to multiple networks through VLAN tags. Also, you have your networking provisioning CLI, which today we use the GoDPU project of OPI. And both the networking provisioning CLI and the VPN gateway CNI, they use the VPN gateway gRPC API in order to configure the different objects on the OPI VPN bridge. And by objects, I mean the VRF, the logical bridges, the bridge ports, and the SVI interfaces that we have talked before. The reason that you see different coloring schema on this slide is because the blue boxes are provided by the different vendors that they have the IPU DPU device, and they are vendor specific. The green boxes are existing open source projects that we leverage and use in order to fulfill our needs. and the yellow parts are vendor agnostic components that we target to upstream to OPI. So this is the target architecture. And let's move on now to the main focus of this meeting, which is the OPI EVPN bridge architecture. It is this component on the red cycle. So here we see the architecture of OPI VPN bridge. With the yellow color, we depict the core component of OPI VPN bridge application. With the pink color, we have the vendor provided component. Those are components that needs to be provided by each vendor, which depends on the card that you have underneath. And also we have an extra module which is called Netlink Watcher. That is a choice of a vendor if it wants to use it, if it wants to use the Netlink Watcher that we provide, or wants to actually use some Netlink Watcher that he has developed. And this is totally on its choice. So let's start from the modules. We can see that we have modules that belong to the slow path. The modules are those down here, and also we have modules that are responsible for offloading, for configuring the fast path, and that means they are used for the offloading purposes. The first module is a general Linux module. This is a core component of OPI VPN bridge, and it is used in order to configure the different items in the slow path, in the Linux slow path. For instance, configure Linux bridges, VRF, several interfaces that we have there, and this is common for all the vendor. So they doesn't carry any vendor specific functionality. So that's why it's a core component for OPI VPN bridge. Then the next module of the slow path is the vendor Linux module. This is a module that is responsible for configuring the vendor specific part when it comes to the slow path. And an example for this is that each vendor maybe have different representative interfaces that they use, and because this is specific for each vendor, then we need to have a vendor Linux module to be provided by the vendor in order to handle those specific cases when it comes to configuration down on the slow path. Then we have the FRR module. This is a module that is also a core one on the OPI VPN bridge, and it is responsible for configuring the FRR daemon that runs on the Linux slow path subsystem. And then if we move on to the offload part, I will start from the vendor module, which is also provided by the vendor of the IPU DPU card, and it is responsible for configuring the hardware pipeline, the fast path down on an IPU DPU. And of course, we have the Netlink Watcher that I will talk a bit later about this. Then all those modules, except from the Linux Netlink Watcher right now, they subscribe to a subscriber framework that exists inside the OPI VPN bridge. And they subscribe there in order to receive notifications when an intent gets created and we need to realize that intent through configuration on the slow path and the fast path. So the different modules they subscribe to the framework. And now let's go through the creation of an object in order to understand the architecture better. So let's assume that we create a VRF protobuf object through the API. So we will use the CLI at the top in order to create that gRPC call for the VRF. Then the gRPC call through the VPN gateway API that we leverage will go to the gRPC server. The gRPC server will take that protobuf object and will translate that through the translation component inside the InfraDB section, as we call it in the OPI VPN bridge, will translate that protobuf object to an internal domain object of InfraDB. So the protobuf object, the protobuf VRF, will be translated to a so-called IFRA-DB VRF, and that new object will be stored then through the storage library to the database, to Redis, for instance, if we use Redis DB. Yes, so when that happens, then a VRF has been created, but not realized. So that this is what we have created a VRF intent that needs to be realized. When that intent gets created in the database, a task for the realization of that intent gets enqueued in the task manager. So the task manager dequeues that task and tries to realize it. So what it will do, it will actually notify each of those modules that has been subscribed to receive notifications in order to realize the intent down on the Linux low path and fast path configuration, and also FRR. So when all the modules receive the notifications and realize the intent, when the configuration is finally there, then the intent has been realized. The status of the intent is success. The status of the VRF is success, and the whole thing is a happy situation. Then we have also the Netlink Watcher, and what the Netlink Watcher does is that actually polls the slow path Linux subsystem for any dynamic configuration. So for instance, just to give you an example to understand, when we have a VRF and we BGP peer with some P router through the VPN gateway functionality that we have in the IPU, the new routes are learned on that VRF routing table. So new routes are installed in VRF routing table, and the Netlink Watcher actually polls for those new configuration that happens in the routing table. It sees that we have a new route, for instance, and when it does that, it notifies the vendor module in order to add additional configuration to the fast path and to address the new route that has been installed in a slow path and adapt the fast path based on that. So this is the different architecture, the architecture of OPI VPN bridge. And let's move on now to say a bit more and highlight the flexible modular design that we are following. So let's take three situations. The first situation is when we have an IPU card on our single server. The second one is when we have any XPU card. It can be an IPU, it can be a DPU SmartNIC card. And the third one is where we have a CI environment, as we have today in OPI VPN bridge, and as we have today in OPI VPN bridge, where we don't have any card underneath, but we have a Docker Compose environment just for testing, and this is our CI environment. And this Docker Compose environment also has its specific Linux configuration that we need to address. So in the IPU, XPU, and CI, you can see with black color all the common components that we use, and they do not change on those three different cases. So the Linux general module, the FRR module, and the Netlink Watcher, when you have a SmartNIC card, are common for all the cases. The only modules that change are the Linux IPU module and the IPU offload module for the IPU case. On the XPU case, you have the Linux XPU module and the XPU offload module for the arbitrary card that you have underneath. And also for your CI environment where you don't have any card, you have only the Linux CI module, which takes care of the specific of your Docker Compose environment, for instance, that we have today. So this depicts the flexible modular design that we have adopted. So if we go through a call of creating a VRF, just to give you an example on how the system behaves, so we use the GoDPU program that we have today in OPI, and we make a create VRF call. The name, we define the name of the VRF, which is blue in our case. Then the VNI for the layer 3 VPN, which is the 1002. The loopback IP of the VRF, and the VTEP IP that is the one that will be used for the VXLAN encapsulation and decapsulation. So we make the call of creating the VRF, and the answer is and the response is that the VRF intent has been created. You see the name. Up here, you see the operational status, which initially is down because the intent has been created but has not been realized yet. So initially is down. You see the VNI, the VTEP, the loopback parameters that we have there, and also we see the component status. So each of those modules that we have presented in the previous slide will try to realize the intent that we have just created, and they will report also the status of this operation. So initially, they have not realized any intent, so the status of its module here, of its component, is pending. So you see LGM, LVM, FRR, and IPU module, all they have pending status. If we just wait 1 second and then do a go DPU get VRF by name blue, the VRF will be the response will be the VRF object, where we see that right now the operational status is up because the intent has been realized by our architecture, and the different components, they have their own status there, which we have all of the components, they have a success status, and also they have an extras field there, which is called details. And by details, the different components report to the user what are the different items that they use when they did the realization of the intent. So for instance, the LGM reports the routing table that has used the routing table number, and the FRR on the detail section reports the route distinguisher that is used, the router MAC, the import and export route targets, and also the local AS. So we see how we create an intent and how we realize that intent through the components that we have. So here I have some sequence diagrams that you can follow when I will share this slide deck, but for now I will just go through a create VRF example and the netlink module example for that same create VRF in order to just give you some context on how this thing works. So, but the rest you can just follow by yourself. Before I go there, I would like to say that the whole architecture has been created with resiliency in mind. So in case that we have any power cut and the OPI VPN gateway bridge goes down, when it comes up again, it will replay the status of the object from the persistent database in order to bring the system up to speed again on the state that was before the power cut. I just wanted to mention that. So if we go to the first diagram, which is a create VRF example diagram, we can see the different components up there. We have the gRPC server, the InfraDB, the task manager, the subscriber framework, then the storage library and the database. Then we have the different modules, FRR module, general Linux module, vendor Linux module, and vendor module. And we have also the different subsystem, which is the FRR, the XPU fast path, and the XPU Linux slow path, as I have presented before. So if we go through a create VRF call, for instance, so the user creates the protobuf VRF, then the gRPC server translate, use the functionality of the InfraDB components to translate that protobuf object to InfraDB domain object, InfraDB domain VRF, as I have said, and then moves on to create that VRF domain VRF intent into the database. So we take a global lock. Then the InfraDB contacts the subscriber framework in order to fetch all the modules that are responsible for realizing the VRF intent. The subscriber framework sends back those modules. Then the VRF intent gets updated with those modules, and finally it is stored in the database. And when this happens, then a task for realization of that intent gets created on the task manager queue. And finally, we return back to the user that the VRF has been created, the VRF intent has been created. In parallel and in a different thread, the realization of that VRF intent is undergoing. So in the task manager thread, we dequeue the task of realizing the VRF intent, and we start to notify the modules. So the task manager will notify first the general Linux module. The general Linux module will actually get the notification. And what we'll actually do is that it will fetch that VRF InfraDB intent from the database, will apply the Linux configuration to the slow path, and then it will update the status of the object from its perspective to success. And then the task manager will just wake up again and notify the next module, which is the vendor Linux module, and then wait again. So then the vendor Linux module in its own thread will actually take again the VRF InfraDB object from the database. It will apply the vendor Linux specific configuration on the slow path. It will update again the status of the InfraDB object to success, and the task manager will move on to the next module, which is then notify the FRR module. So the FRR module will again apply the FRR configuration to the FRR daemon, and so on and so forth. So when all those modules get to success, then it will move on to the last module, which is the vendor module. The task manager will notify the vendor module. The vendor module will apply the fast path configuration down on the XPU hardware pipeline. And if that is successful, it will update the status. The task manager after that will see that the task has been realized completely and successfully because all the modules that are involved in that realization has done their work, and it will just drop the VRF realization task as it should be because everything is done. So this is what is happening in the background when we create a VRF intent. We create the VRF intent and all the system asynchronously tries to actually realize that intent. And now let's talk a bit about the netlink module. So we have also a netlink watcher, and as I said, we have some static configuration, but we have also some dynamic configuration that we need to take care. So when we learn new routes on that VRF through BGP protocol, we need to actually pass that configuration and configure the hardware pipeline, the fast path, when we have those dynamic additions. So let's assume that we have a new route that gets advertised and installed on the created VRF in Linux. So the netlink watcher will continuously poll for changes in the Linux VRF configuration state, and it polls the state, and also it fetches the InfraDB VRF object from the database. Finally, it will create a netlink database snapshot, which includes the latest polled information from Linux, plus some annotated information that gets learned by the VRF object that we fetch from the InfraDB. And it will create a new netlink database snapshot with that. Then this newly created netlink database snapshot will be compared with the old netlink database snapshot. And if we find any difference there, any deltas, which in our case we will, because we have a new route that has been added in the Linux VRF, if we find any delta, then the netlink watcher will actually notify the vendor module that it needs to actually configure some extra rules down in the fast path because a new route has been added in the slow path. So this is how we address with this architecture the static configuration, which is like create of a VRF intent, and also the dynamic configuration that we have, and an example of that is learning routes through BGP. So these are the different sequence diagrams that I have. I have two additional diagrams that explain the requeuing that happens on the task when some module fails to apply a configuration. You can check it out offline to see how that is working. It is explained here. And also I have a resiliency sequence diagram which explain what happens when we have a power cut, and then when the system gets up, how we replay the whole state of the persistent database in order to bring the system up to speed and in the same state as it was before the power cut. And finally, I have here some references. Those are links that you can follow, you can click in order to follow the different development efforts that happens today. Our plan is to create the first pull request of the OPI VPN bridge that addresses only the slow path configuration initially by the end of March. And that first pull request will include the OPI VPN bridge code. It will include also some changes that we have done to the VPN gateway API, and also some changes that we have done to the Go DPU project. And the VPN gateway CNI, if we will try as a stretch goal to actually have the VPN gateway CNI also in that first pull request, but if not, we will definitely have it with the second pull request that will happen somewhere in second quarter of this year. This is the presentation, the slides that I have. We still have 15 minutes, and I would like to thank you, and also you are free to give me any feedback or to answer to give me any questions that I can answer.
Thank you, Demetrius. First question, are you going to share these slides?
Yes.
Okay, so let me ask one more question that I had in mind. You mentioned the routing tables. Are the routing tables on the ARM cores?
Yes.
So you're
Exactly.
maintaining them on the ARM cores and you're refreshing them with some sort of a daemon?
Correct. Yeah. So the routing tables will be installed in the Linux slow path, and by Linux slow path I mean the ARM cores of the IPU, where you have a Linux distribution there, right? And those new routes are getting injected there in the ARM cores, and the Netlink watcher will actually dynamically read that information from there.
Okay, and since I have the mic, one more question. How are you working to expand this work to work with other IPUs, DPUs?
Yes, this is that's why we have this flexible modular design, right? So this vendor Linux module, vendor module, and the Netlink watcher can be provided by the different vendors for their own cases. So if right now we are working with the Intel IPU, okay, so we have a vendor Linux module for the Intel IPU and vendor module for the Intel IPU, and a Netlink watcher that we provide that can work with all the IPUs, all the IPUs, DPUs. Doesn't need to be provided by the vendor, but if they want, they can actually provide their own Netlink watcher that is on their thinking. But if NVIDIA, for instance, comes with their own DPU, they need to come also with a vendor Linux module for their own DPU and a vendor module for their own DPU. So when we have a new card, the vendor needs to provide also the module in order to address the different changes, the specifics of this card. And by specifics, we mean the vendor module that is responsible for configuring the fast path of the card, and also the vendor Linux module that is responsible for taking care of the specifics of the card when it comes to slow path. For instance, the different representative interfaces that maybe in NVIDIA, they use a different representative interfaces design than the Intel IPU, for instance.
So how does Ericsson work with the other vendors to ensure that that it's working? I mean, let's assume that NVIDIA or Marvell come in with those tools.
Mm-hmm.
Do we have anybody from Ericsson who's going to work with us to implement it? and to make sure that it
Right
works?
now, specifically, no. But if we upstream that, and any vendor actually is interested about the VPN gateway functionality that we offload, right? They can work with us in order to add to address their questions, and also add the extra functionality in order to have an VPN gateway offloaded to their own card, for example, Marvel or DPU. So that's why we open source these things. So different vendors can actually come in and say, we're interested for that. We would like to actually adapt everything to work also in our cards.
I'm assuming that all the vendors will be interested because that's the idea of OPI.
Yes.
My question is, do they turn to you? Is it you that they speak to?
They can if they want.
Okay, thank you.
Thank you.
I have one question regarding the Kubernetes. The secondary interfaces that we have created for the pods, which is managed by the EVPN gateway CNI, does it support the services model? Is it something that scales across multiple hosts, using the service concept?
No, it's like how the SRV CNI, for instance, work today, or the OVS CNI. So here we have like a VPN gateway CNI that works like more or less the same way as the different CNIs that we have out there today, and those CNIs are local to the node, right? So you have a CNI binary local to its node in Kubernetes, and through Multus, the CNI binary attaches virtual functions inside the Kubernetes pods. And actually, our CNI does two things. The first one is attaches the virtual functions to the Kubernetes pods, and also contacts the OPI VPN bridge in order to create a bridge port object through the gRPC API, and then the OPI VPN bridge configures the hardware pipeline in order to have external network connectivity to those attached secondary virtual functions of the Kubernetes pod. So
Okay,
it's
I mean,
not
the
it's not in
SRV
a service concept. It's like the same way that all the CNIs work today.
right, but if I have multiple hosts with their multiple IPU DPU cards, will the load be distributed using that service IP address?
This is where right now we're talking about a single server deployment. So we have some designs that we have like multiple servers, but right now they are not fulfilled. So right now, if you have just a single server, then you have a single server. Yeah, you don't have any load distribution between different servers.
I see. Okay.
Yeah, but we have designs for multiple servers in a site, and how those servers can work together. So maybe in the future, we will have like more information about this.
Okay, and one more question about the data plane interface that passes through the ARM cores. I'm assuming these are mostly exception packets, or like some of the control packets, like BGP sending some of its peering
Yeah,
related information.
yeah. I mean, we need, as you know, those are control planes. What we have in ARM cores, we use them as control planes. So the slow path, it is used for exception packets, as you are saying. So for instance, if you need to do some Mac learning, stuff like that, then you have the packet comes inside the programmable hardware pipeline, that it gets forwarded as exception packet to the ARM cores. The learning happens, and then when the neighbor gets created in the ARM cores, then a new rule gets installed in the programmable hardware pipeline. So the next packets, they can actually match in those rules, and they don't need anymore to actually be forwarded to the ARM cores, but they can actually forward it directly through the programmable hardware pipeline.
Okay, so that means the database is being updated only in the ARM cores. It's not percolated to the routing database in the host. Because
Yes.
I don't see that connection.
Yes.
Okay.
Yes.
Okay, thanks.
So one question on the ARM cores, instead of Linux low path, if we wanted to use something like OVS DPDK plus for on DPDK, is that a possibility?
Right now, we haven't investigated this use case, but yeah, I don't have an answer right now. Maybe it's possible. Yes, it should be flexible and probably you can do that, but we don't have any studies around it, I will say.
The second question, the Go DPU has to run on the host, or can it run outside of the
No, you
host?
can run it anywhere. The Go DPU is just a gRPC client, so if you have connectivity to the gRPC server somehow, then you can run it anywhere. I just put it in the host right now just for simplicity.
So you use a dedicated connection between the host and the IPU using some.
Yes, you have some interfaces that are actually, you have several interfaces that are exposed to the host from the IPU, and one of those can be used in order to have this gRPC communication for the server, between the server and the ARM cores.
Thank you.
If no one else has any questions, I have one more. Going back to the same routing table. So you have one routing table in host, another in ARM core, and the two are disconnected, but they both are feeding into the hardware pipeline. So
No.
it's having a, no?
No. The host routing table play no role, really. The ARM cores routing table are the ones that are offloaded to the IPU, to the hardware pipeline.
Okay, so there is a connection from host Linux routing IP tables going to the pipeline. What kind of packets are we seeing on that?
The only packets that we see is it's for primary external networking connectivity. So when you try, for instance, you have like a load balancer IP or whatever on that primary virtual function, that IP gets advertised, for instance, to the PE router on the data center, and you can actually ping it from the PE router on the data center towards that. But the Linux routing IP tables and the primary CNI and whatever right now have on the primary CNI side, and when it comes to the ETH0 interface, is not offloaded to the programmable hardware pipeline.
Okay, so it connects to the VLAN bridge, but it's actually not connected. It goes all the way exposed as a separate interface on the IPU.
Yes.
Okay, so it's a bypass for the entire path. All the blue boxes are bypassed in that case.
No, it's not. It's not bypass. I mean, in each server, right? You have an interface which is your external interface for your Calico CNI, for instance. This interface, this external interface, is the primary virtual function.
Right, but
So
it is going through the XPU and
yeah,
it is going through all those blue boxes. So I'm wondering what is happening in those blue boxes then, if it's not using them.
it used those, but it just used those to actually. So maybe your primary virtual function is connected to, like, if you have like a typical deployment, your primary virtual function maybe goes like through a VRF in your data center gateway, right? So that VRF or the bridge that is connected before that VRF, it is represented here by this programmable hardware pipeline. So that functionality is represented on the programmable hardware pipeline. Your programmable hardware pipeline today is your EVPN gateway data center gateway.
Okay.
It plays the role of your data center gateway.
Okay, so it's getting routed twice, once in the host by the Linux routing table,
yes,
and then it is again getting routed as per the ARM routing table, which is, okay.
Yes. Any more questions? Okay, I know that all these were too much to follow in just one sitting, so I will share the slides. I will welcome any feedback that you have on the OPI VPN bridge design. As I said, we have the first implementation on that, and it will be fully upstream through a pull request by the for only the slow path components by the end of March. But if you have any feedback that you can give me now, anything that you don't like, any objections that we can discuss and address, please do not hesitate to actually ping me on the Slack or just send a mail to me. I would like to thank you for your patience and for the interested questions.
Yeah,
And-
thanks a lot, Dimitris.
Thank you, Joe.
Yeah, we can, again, if you have questions where you want to discuss in person, we can add a follow-up discussion to this next week on the TSC call as well. So just, we have 5 or 6 communication channels, pick one and make your desires known. If you have any topics for next week, let me know and I'll put them on the agenda. All right, thank you everyone for the.
Joe, just a final question. Where can I upload those slides? How should I send it to you? Or?
That is a good question. Because the problem is we're sharing everything in Git. Git can deal with uploaded PowerPoints okay, as long as you're not, trying to revise them all the time. We have a website. Paul,
we've got Google Docs, but that's difficult for some people to access.
Why not put it on the general Slack channel?
Because there's no long-term record of it.
Well,
we don't
You can put it in the API Git if you want, Joe.
That's probably the best place for it. Is actually the best place for it is the Git for this project.
The OPI VPN bridge. Git.
Yeah.
Okay.
That's the best place for it because that's what it's describing, and this is great documentation. And yeah, I know it's not markdown, blah blah blah. Just put it there.
Just make a doc folder and put it in there.
That's correct.
All right, I can do that. I will create a pull request in a doc folder.
Please share a link to that as well in Slack. Please share just a link.
Absolutely. Yeah, sharing the link in Slack is a wonderful suggestion. That's great. All right.
All right.
Yeah, so put it there because that's where it belongs. I agree with Mark on doc folder, and Mark will just approve it. This is just a pull request to follow the process. Yep. All right. Thanks, guys.
Thank you.
Thanks, guys.